It's okay? Okay, good. 그러면 So welcome to today's invited talk at the AI Institute at Seoul National University. I'm very pleased and honored to introduce Professor Ken Forbes from Northwestern University. He has graduated from MIT in the peak of classical AI time. I see it's 1984. You got the PhD from MIT and then actually he has been professor at UIUC as well, and then moved to Northwestern. I think Ken has been pursuing quite a long time, and the very unique, I think, pursuing the qualitative reasoning and analogy making and machine learning as well. Especially, I think he's pursuing understanding human cognition and cognitive modeling, and it's used to building really intelligent machines, AI. So maybe today's talk will be very unique in that sense that it's an intersection of cognitive science and AI. So please welcome Professor Forbes. Thank you.
Thank you. Thank you. That was a great introduction. Let me just make sure this machine is happy. There we go. That's Luxor, by the way. So I'm going to tell you about work that Deidre Gettner and I have been doing on generalization in both people and machines. And what I'll do is I'll start off with looking at qualitative representations as a kind of ontological support for generalization. And I'll mention QR more broadly, but then I'll focus in on actually computer vision. Does it sound okay? Okay. And I'll tell you about the idea of the hybrid primal sketch, which is something we've done a lot of work on. And then I'll talk about analogy as a process of generalization. I'll tell you about structure mapping theory, the analogy stack we use to implement it, and I'll again go in depth on how the hybrid primal sketch has been used to do sketch recognition. Then I'll step back and look at things a bit more broadly and talk about what we call the Continuum of Knowledge Hypothesis, which is a hypothesis about the overall large-scale structure of human knowledge and a very different path for how to build knowledge into AI systems. And I'll end with some conclusions and open questions, and even mention a couple of resources if you want to get involved in this sort of research also. So, qualitative representations. So, if you think about continuous phenomena, one thing people do is they talk about them in terms of phase space. So this might be the volume of behaviors corresponding to a particular Ah, that's a little better. Okay, how's that? Okay, so water can have this whole range where, 12 degrees versus 13 degrees, not so different. And the region of space above a table. So I set this down here and it's fine. If I put it a little too far over there, it's not going to be fine and my backpack's going to get wet and I'll be very unhappy. It won't be good. And qualitative representations provide causal models that operate with very little data. So you add heat to a liquid, its temperature increases, all else being equal. You do it enough, it hits the boiling temperature. And so it turns out this is synergistic with analogical reasoning because analogy is very good at supporting rapid qualitative reasoning. And qualitative representations, because they abstract out details, help support analogical reasoning. So if you look at traditional math like F equals ma, lovely equation, you can send people to the moon and get them back home safely with this. It's great for certain purposes. It got invented for things we don't do, right? And so in terms of using it, you need a lot more details than you normally have in a common sense situation. So you get these unrealistic input requirements. Whereas if I'm just pushing or pulling something, one of the things I can do is learn that the acceleration depends on the force. That is, the more the force is, the higher the acceleration is. The lower the force is, the lower the acceleration is. How much? We don't know. That's why it's a qualitative relationship. So there's ambiguity in qualitative reasoning, but that's okay, because the world's going to tell you pretty quickly how much things shake out. So you can use these qualitative models to capture a lot of human phenomena. sketch assertions for bear and grouping algorithms, figuring out the outline and the muzzle and the eyes and the nose. So this was a revolution in vision. Before, people were basically stumbling around and having a great deal of trouble. And this idea that you are computing some intermediate representations, and that there's a whole series of those representations, really changed the way things worked. So if you look at computer vision today, in fact, many of Mars' theories held up. The whole idea of edge detection, the whole idea of having stages where you put together a more and more comprehensive set of visual analyses seems to be holding up just fine. Some of the biological predictions about this particular area in our visual cortex does this particular job, those haven't worked out so well. Okay, that's fine. I mean, anyone remember how many types of neurons there are in the brain?
10 to the 11.
10
to the 11.
That's the number of neurons, types of neurons.
Types of neurons. Maybe 20?
Thousands. That just came out in Nature. Thousands. It's, right, so 20 was a great answer 3 years ago. It's no longer a great answer. And biology changes a lot, right? It's, when you're trying to make bets across so many levels, it's hard to do. Now, when you look at deep learning, it's used a lot in computer vision these days. New edge detectors and object detectors, segmentation. And now recently, people have also done large language models with multimodal additions. These tend to be reasonable. These tend to not be so reasonable. Massive confabulations, right? Massive confabulations. And the limitations in both cases are batch training and opaque models. So that's irksome. So what do you do instead? Well, our idea is the hybrid primal sketch. So we're going to exploit advances in computer vision. So we use object recognizers and segmentation algorithms as a stand-in for the raw primal sketch. Are these biologically plausible? We don't know, we don't care. We're being engineers for this part of the model, okay? That part of the model. The higher level parts, though, we do care about scientifically, and these exploit advances in qualitative visual representations and advances in analogical learning to give us incremental data and training efficient learning of inspectable models. And so we're going to get the best of both worlds by hybridizing. The lower levels, uninspectable. The higher levels, very inspectable. Okay, now the higher levels are bundled up in a system called CogSketch, which, by the way, you can download and run on any Windows box. So it's both a cognitive science research instrument. So here, for example, if you download CogSketch, you get all of the old Evans geometric analogy problems. You ask it to solve this problem, it'll light up showing you how it's analyzing the stuff, and it'll basically draw in what it got as the answer. Again, this actually predicts human reaction times in terms of the performance on this task. We don't bother with error rates because they're so easy, everybody gets them right. Just about everybody gets them right. But it does predict reaction time performance. Oops. This is an oddity task done by Dehaan and Spelke with Americans in Manduruku. You're supposed to pick the odd one out. Again, it's a task where you use qualitative representations and analogy. We have the same pattern of errors. What's hard for the software is hard for people and vice versa. And by doing ablation studies in the software, not the people, obviously, by doing those ablation studies, we can actually explain some of the cross-cultural differences. Raven's progressive matrices is the single best test of human fluid intelligence. The CogSketch model of Ravens, in addition to, again, replicating human performance in detail, is in the 72nd percentile, so it's better than most adult Americans at Ravens. Okay. So we get human level performance and explaining psychological data, which means we've used it as a platform for new kinds of educational software. So the design coach helps students practice giving explanations. You know, there's a social threat. If you explain something to your friends and they don't understand, if you're explaining something to a machine, okay, it's a machine. You do it again and you fix it. So it actually turns out to cut anxiety about explaining things. And the one that's got the most pickup is sketch worksheets, where basically at any time the student can ask for help and get feedback. And the feedback's generated by analogy, based on comparing the teacher's sketch to the student's sketch. So that's deployed software. It's very popular in geoscience, for example. Now, let's open up the hood. So the basic thing that CogSketch sketches are made out of are glyphs that combine ink and what it represents. Here's a little piece of a sketch by one of the geoscience faculty. It's a worksheet for the carbon cycle. So they're supposed to mark on this background, this is the ocean, and that's an example of an entity glyph. So you've got something representing the oceans, and you've got this ink that describes it. Relation glyphs describe relations between objects. Here it's a flow from carbon dioxide from the ocean to this other thing, which is the atmosphere. And the third kind of glyph are annotation glyphs to provide information about other glyphs. So the atmosphere has 750 petagrams of carbon in it. Okay. So that's a very flexible language, visual language for talking about things. Now that's humans drawing, right? Now for computer vision, of course, we want to automate that process. So you can have an SVG file, straight old vector graphics, and there's a little converter that converts that into the polyline format CogSketch uses and drop it in as a glyph. Or you have a bitmap file of some sketch, and you use PoTrace and OpenCV to get basically digital ink for CogSketch, and you drop it in as a glyph. And if you have a natural image, well, you've got deep learning recognizers and segmenters that carve things off and say, well, that, inside that, is something labeled as person, and now you've got your ink and a word, which then can get turned into a conceptual interpretation and dropped into CogSketch as a glyph. So now you're beginning to see that basically we have this ensemble. And so the hybrid primal sketch basically has a ton of visual components. And by the way, I haven't shown you everything on here. We can also use connect video input and do the same thing with that. Okay. And then those get translated into glyphs, and then we do analogical learning to learn stuff. So the hypothesis is visual qualitative relations plus analogical learning gives you data efficiency and interpretability in visual tasks. I'm going to show you evidence for that. But now, of course, we have to get into how analogy works, because that's our learning mechanism here. So now let's talk about analogy. So structure mapping theory. So imagine you're learning about solar energy and someone's trying to explain the idea of leaks. So they say, well, okay, look, you can have water, you're trying to fill this bucket with water and it's got leaks. And so I have here a predicate calculus version of that picture, or at least part of that picture. And I'm comparing that to a situation where I've got a house where if I have more insulation on the roof, then there's less heat leakage, just like having smaller holes here. And so I have, again, a description of this, and the analogy consists of a set of correspondences that say what goes with what, based on the predicates aligning. Then they suggest arguments that align. Those give rise to candidate inferences. So you project that the object of state change is going to have a reduction here because I've got more insulation here. And in addition, there's a numerical estimate of how good the analogy is. So mapping consists of these correspondences, candidate inferences, plus numerical similarity score. So we've got a large body of psychological evidence for this theory and evidence for medium-level vision up through reasoning and problem-solving conceptual change. The same processes are used in humans. And we've also now been simulating them throughout that same range in AI systems. So it's a very tightly coupled story. Now, let me show you a couple of things about analogy that may surprise you. The first is that the same computations are used for both analogy and similarity in humans. Structure mapping over relational representations. So dot products of random matrices or vectors, not what most human similarity judgments are like. Is it like all human similarity judgments? That we don't know. That we don't know. So for instance, in language, there's a thing envision this thing called setting, which is core statistical properties of a visual scene. And differences in setting is what controls eye movements. Okay. So there may be some lower level notions of similarity that occur across different kinds of things, especially in the perceptual world. But by the time you get to conceptual materials and even high level vision stuff, it's the same process. Second, difference detection is based on similarity. It's faster to detect things are different when they're very different, but faster to name a difference when they're very similar. And it turns out the reason is because the way the SME algorithm works. So here's my base and here's my target. And it works by making a set of match hypothesis forests, little guesses, some subset of which are going to turn out to be consistent, and the correspondence is in a mapping. But before that, you've got this inchoate set. If that set is small, then the two descriptions are very different. If that set is large, they're very similar. So it's faster to say things are different when they're very different because you look at the size and it's like there's nothing here. Yeah. Okay. The fact that I've got a lot of things in the forest doesn't necessarily mean I'm going to get a good match at the end. That's why it takes longer to do. But then the faster to name a difference, because I've got a big set of consistent things to pull from, then the differences that are easy to name are called alignable differences. They're tied to the candidate inferences. And so that's why it's actually easier to name a difference when things are very similar. One of those lovely little phenomena that's hard to explain unless you actually look at how SME works. And then analogical comparison, especially within domain comparison, often happens unconsciously. So some of my friends will say, well, analogy, that's a system 2 thing, right? That's a very conscious thing. Yeah, it turns out the same processes are happening all over cognition. Now, vision is not a system 2 thing, right? And yet, I showed you those visual problem-solving examples that are operating exactly using structure mapping. And so when you think about it, when you do conceptual stuff, like reading a story, you think, reading a story, I'm understanding the story. I'm understanding the story based on what's there right now, right? Well, it turns out Debbie and her collaborators can make you interpret a story differently depending on what they gave you to read several days earlier. Because it turns out there's some parts that are ambiguous. And there's 2 different ways you could resolve that ambiguity. And if you give somebody a story that would push you in one direction versus another, you can get people to be pushed in that way. And if the stories are very similar, it can be 2 or 3 days later, and they haven't a clue that that's what's happened. Okay. One of the papers on this is called Resistance is Futile. Okay.
So can I ask you a question?
Yeah.
Do you think that this applies for the animals also?
I think a lot of it applies to animals. Now the question is, can they do amodal and cross-modal analogies? Probably not. I think a lot of the stuff may be very modality specific, but that's a guess. So here's the big picture about analogy. Structure mapping engine that I've just been telling you about. Some new description you're trying to learn about. Some description you're applying. You're taking candidate emphasis from here to there. Now, how do you get those descriptions? We have a model called MacFac. Many are called, but few are chosen, that retrieves things based on a two-stage MapReduce process. That's coming out of a large knowledge base. Inside that large knowledge base are not just examples, but also generalizations. And Sage, when it gets a new example, mushes it together, compares it with the best thing it can find using MacFac, and if it's sufficiently close, assimilates it. So what it's producing are basically probabilistic schemas that are partially abstracted. And there's even a working memory version that generalizes, which I'm not going to show you due to space limitations, although I will bring it up a little bit later. Okay, so here's how analogical generalization works. So concepts are modeled in what we call generalization pools, and they consist of generalizations, i.e. probabilistic schemas and outliers. So generalizations are incrementally constructed from examples. There's no logical variables, right? Usually when people talk about generalization in machine learning, they talk about putting in variables. We're not talking about that. So concepts get built up incrementally. So you get the closest match to a new example by MacFac if it's long-term memory, linear search if it's based on recency, if it's in working memory. And if the assimilate is over a threshold, you assimilate by combining the overlap that SME computes. If it was a generalization before, it updates that generalization by changing the probabilities based on now what the new frequencies are. Creates a new generalization if an outlier was retrieved, and that's how the process works. Okay. And if it wasn't close enough, then you add it as a new outlier. Today's outlier may be the seed of tomorrow's great new generalization, depending on what the distribution looks like. So it's entirely incremental. It's like k-means with outliers, except you don't have to say what k is. The algorithm figures that out. Now, we've used this in a lot of things. Obviously, I'm not going to make your eyes glaze by reading this, but happy to talk about any of them offline. Things that are particularly different. Recently, some work on legal reasoning, where Joe Blass had to tweak Sage quite a lot to make that work properly. Counterterrorism was kind of interesting and fun. Analogical QA training. But anyway, we're just going to focus on vision today. So, how do you do classification? Well, you've got these generalization pools, one per concept, right? And these can be viewed as a case library. So, I have a new example to classify. I put that into MacFac as the probe, and I use these, the union of these, as the case library. And there's going to be some example come out that's the closest, and I'm going to take whatever label was associated with that pool, and that's going to be my classification. So basically, I reduce classification to retrieval over generalization pools. Okay, so now we've got all the pieces in place. We can get glyphs in, we can throw them into Sage and do learning. So we're almost there. So, for sketch recognition, one of the problems we'll look at is the classic imness problem. So Jan LeCun and others basically dumbed down what were high-resolution images to really coarse-grained vectors, because that's all the CNNs at the time could do. Okay, but it's a standard corpus, so you got to do it. The Technical University of Berlin corpus, which was already in SVG vector graphics, and a set called the coloring book objects, which consists of bitmaps. So here's one from the coloring book objects data set. The coloring book objects data set, as you'll see, has only 10 examples per category. It is designed to be torture for deep learning systems, right? If you have a data-hungry system, this is not your friend. And so the hypothesis is analogy over qualitative representations provides data-efficient learning of expectable models. So, one or two more details, and then you're ready to roll. Okay. So, how do we actually describe the shapes? So, Irv Biederman had this great idea of recognition by components. So here's an analysis of a fish, and it computes the medial axis transform, you can see here, which is a very, very old idea, for every edge cycle. And we segment edge cycles into qualitatively uniform pieces. So medial axis transform, it turns out, there's been some recent evidence now that says that's actually how humans are describing shapes. Take an iPad with a shape on it, walk up to somebody in Times Square and just say, point at the shape. They touch it somewhere. They almost always touch it, along a medial axis line. Now, people made fun of Bloom's brush fire algorithm because if you have a little tweak at the corner of a shape, it really changes the way the axis goes. Well, the same psychologist team took those distorted figures and took the iPad to Times Square back again, and it distorts in the same way. Okay, so the brush fire algorithm really looks like something to do with how people are computing it. So, wow, who knew? I mean, I would not have predicted that. Okay, no way would I have predicted that. So then now, to carve things up into pieces, you look for concavities, and you basically add a segmentation line at each of those closures. And so now you're getting, again, small differences in the shape aren't going to make a big difference here because you're using scale also to help segment this stuff. And so differences between particular individuals get washed out. That's part of the joy of qualitative representations. Now, this also gives you a way of putting in some hierarchical description. So here we've got our fish. Here we've got an edge cycle decomposition. And now here is something where you've got cycle 30, that's the outside perimeter. You've got the 4 cycles, 1, 2, 3, 4, and this is the interior cycle. Okay. So now you've got this nice hierarchical description that helps you provide more structure to it. And for complex things, that's really important. Now that, in fact, we did an ICHCAI paper on this last year, part-based hierarchical analogical learning. You take the edge cycle decomposition, and there we have this for the airplane, and you do encodings and build analogical models at all 3 levels. And you start coarse, and the large number of categories that you might use there, those become what you hone down to. And so you get to finer and finer grain as you go down. And actually then you combine those things. And the details don't matter for this particular talk. But now let's look at the results. So MNIST, 10 concepts, right? 10 digits, 6,000 examples of each. And we want to do data efficient learning, so 10 examples per digit, we're already at 55% accuracy, 100, 76, 585, but that we top out there. Give us more, we don't do any better. I don't know for sure why that is, I have some guesses, but if you look at Lynette, it needs 1,000 examples per digit to do better than chance. It reaches 98.3% accuracy after 1,500 examples and 20 epochs. This is a single pass through the system, right? So in other words, we're getting data efficient learning, not as good in terms of ultimate performance, but with a boatload less computation. For the Berlin data set, 250 concepts, they claim it covers all of everyday life. I hope not. Their version of everyday life includes hand grenades and flying saucers. And I hope they're not both in part of your everyday life. Okay. It has very complex things. So for example, things with textures like grapes, pineapples, turtles, pizza, all have textures. Turns out, want to guess how we do textures? You throw stuff into a sage generalization pool, and the things that generalize out, you say, okay, that's a texture. Okay, so you can automatically use sage to recognize textures as well. Who knew? So now we run that, and this is using FAL. So 69.85%, you notice we're doing competitive with everybody down here. And what's the difference between these two? Well, these are using pre-trained models. These are starting from scratch. So if you want data efficiency, these are the things to compare against. If you want to do the task and are willing to do arbitrary amounts of training, sure. Go ahead, train on more stuff. Okay. It also wouldn't surprise me that the pre-training here included this data set because it's publicly available and the people who build these models tend to hoover in everything they can get their hands on. Now, what about the coloring book objects? Here's a sample of them. You recognize this fish, it's an old friend. Some of the animals are wearing hats. Okay, so this is out of coloring books. It really is, they're crazy different as well as only being 10 of them. So here we rock. Then at 5, way below chance. ResNet, way below chance. ResNet 50 pre-trained is the first thing that gets above chance. But simple analogy, just throwing in the whole description at once with SAGE, gets 29%, so it beats pre-trained ResNet. And the hierarchical analogy system gets another 8% beyond that. Okay, so right now analogy still remains, analogy was the top when we first brought out, and nobody's done better than simple analogy in the deep learning community. I'm sure somebody will. Okay, so now I mentioned explainability, inspectable models. Well, so here's, for instance, a wing of an airplane, and this is from the second level down description, and you notice that the part is, these are probabilities, right? So it's a neighbor of one part versus another, depending on the generalization. It's above another particular part half the time. It's, this other part is medium 75% of the time. And here's a front wheel of a bicycle. And you notice now the airplane has 36 generalizations and 19 outliers. These are not tiny models, but each one of them is a set of, each one of them is a probabilistic schema or an example. And so these are actually very inspectable. So what are we doing now? Well, obviously, one of the things you can do is try to use this for multimodal understanding, right? So we've been doing multimodal learning from science texts, and so it makes sense to do diagram understanding. So here's a food web. So an arrow indicates that foxes eat puffins and rats and kittiwakes. Decomposers get us all in the end, of course. Those are various kinds of microbes that decompose stuff. There's structural descriptions, like this volcano. And there's food webs, where you have arrows now. So these arrows don't mean eats, right? This arrow means becomes, right? Or lays eggs or something. But the point is, this is a life cycle. So we mentioned that we're very Catholic in the old sense of Catholic in terms of being willing to use all sorts of modules. So in doing this, for example, here's the output for SAM and ALV9, which is what we've been using for segmentation. And you notice that they do a pretty good job, at least in this diagram, of carving off pieces. And the texts are recognized by deep learning OCR systems. Deep Solo is the one we've used the most. There's another one that Wang Cheng is experimenting with. And so these are now basically being identified as labels, and we're using proximity to say, well, what does the label refer to, right? And the arrows now, remember I talked about relation glyphs, connecting two glyphs? Well, we're literally recognizing these arrows. This is an arrow from the segmentation algorithm being passed into CogSketch as a relation glyph, And CogSketch's algorithm for basically figuring out what the error refers to, which is something that humans gets displayed for humans so they can change it if the system got it wrong. And it's showing you that this is what it thinks that arrow is connecting, which in this case is correct. Not always correct. Doesn't always find all the arrows, for example. Okay, so this is still very much a work in progress. So now we're down to the Continuum of Knowledge Hypothesis. So how does cognition work, big scale? Right? I mean, it's not just that you lock a kid in a room with billions of pieces of text and make them read for 20 to 100,000 years, depending on who you talk to, right? That's just sort of crazy. We have experiences in the world, and these are vast in number. We're having them all the time. They're very concrete. And over time, we generalize, and our culture helps us tremendously, right? Little kids don't just see movies, they get talked to. Oh, look at that, right? And so there's all sorts of feedback we get from our culture. But that culture is forming out of this vast experience robust concepts. If you didn't have this, the culture doesn't help. So Deidre and I jokingly call this the dark matter of human cognition, right? It's the missing mass, the stuff that we know is there because things aren't working if you don't take that into account. And so what happens, we think, is with analogical generalization, you get increasingly abstract, increasingly portable structures. So, for instance, you get semi-concrete knowledge, you get even less concrete, abstract knowledge, and these become more rule-like. So they're more applicable in new situations. In fact, some of the things we do even do add rules. So we've explored this for a while now. I mean, you notice some of these dates on these papers are pretty early, and you might think, oh, dusting off this old idea now, right? See if it's got any legs. Well, we've been actually executing on this big picture for a while now, right? So this isn't a complete picture, but if you look at the idea we had for prototypical behaviors, the portion of Scott's thesis that basically combined by analogy, particular examples, and now starting to learn rules like when does something float? Okay, so learning conceptual models from experience, debugging mental models. I showed you an example of that earlier. Cross-domain analogical learning in physics, problem solving, and looking at novice expert differences in strategy and problem solving. So we've got pieces of evidence, and we're talking about the whole swaths of human knowledge just in physical domains that's too big for any one research group to deal with, right? But you can take measurements at different points and try to see, yeah, the story here actually kind of hangs together. And we could go out and do more physical domains, but we decided to be really bold and say, well, okay, physical domains, let's assume that that's going to work out for the rest of them. Maybe social domains are like physical domains. So the same mechanisms, but some of the representations are going to be a little bit more complex because you've got nested beliefs and all sorts of other funky stuff in language. So here, Joe Blass's work on legal reasoning, analogy and legal reasoning is a great example of the high end of this in terms of more abstraction. Irina Repkina's work on analogical theory of mind, Taylor Olson's work on learning social norms comes in here at the middle. And in terms of getting experience, we've actually built a social bot now that's actually learning about particular people in its environment and building models of them over time. That's very much work in progress. If you're going to be at the talk at Dongguk tomorrow, I'll be talking about the social bot. So just to give you a sense about how this actually plays out, so in theory of mind training studies, turns out you show a kid a box and it's got Fruit Loops in it, and it's Fruit Loops box, that's great. You show a kid a box of Legos, and it's got Legos in it, that's great. You show a kid a box of crayons, you ask what's inside, they'll think crayons. And no, it's rocks, okay? And below a certain age, if you know it's rocks, they'll think anyone else knows it's rocks. And this basically is a little training pattern that you can use to move kids ahead by several years in learning this kind of task. Interestingly, when we simulated this with Sage WM, Arena basically said, hey, you know, when you're doing the theory of mind check problems, I'll bet the one they get right is this one, and only this one. And Christian and Dedry said, well, okay, we never analyzed that. They went back and looked, and she was right. So in other words, a very interesting detail prediction came out of doing the simulation. She and CJ also looked at using language patterns to learn to do theory of mind reasoning. And again, in all these cases, there's some original work and then there's our simulation version. So just to wrap up now. So qualitative representations support human-like generalization. We've looked at this in visual reasoning and recognition, STEM reasoning, conceptual change. There's a lot of areas I didn't discuss, like moral decision-making and blame assignment, strategic reasoning, learning by experimentation. But there's a very general way to do representations. And I've argued that analogy provides human-like generalization, and again, in multiple domains, and there's many more I could have discussed. And so the structure mapping is broadly compatible with human reasoning and learning, and it can be engineered to provide complementary cognitive strengths to human partners. So analogical learning, this is why everybody should be doing analogical learning. Pitch. It's incremental. Even one case lets you draw new conclusions, and analogical generalization promotes transfer. It's data and training efficient, sometimes orders of magnitude less data than deep learning. And single pass to the data versus multiple epochs. So the systems that were doing the TU Berlin stuff, those were 8 to 20 epochs depending on the system, versus 1 for ours. Okay. And inspectable models, probabilistic relational models, are easier to understand than hundreds of thousands to billions of numerical parameters. Now, sometimes in head-to-head comparisons, performance can be lower, but it can also be higher. And again, we have some things in our back pocket that might help with some of the head-to-head comparisons. Now, there's still a lot of open questions. We do not have this nailed down completely in any sense. So just in terms of Sage, here's open questions that nag me, okay? So, when do you keep generalizations? If you generalize something, do you keep the example or not? I mean, we've been keeping them all because what the hell, memory's cheap, and because then we can debug. But if you imagine now a being that's living over a lifespan, in fact, mushing out a lot of these things and not keeping them all is probably a really smart idea. So what strategies do you use to make that decision? As you learn, you encode things differently. That's one of the lessons from the whole literature on novice expert performance. So what happens to the generalizations? Do you just basically lose access to the things that were encoded in the old ways? Do you re-encode them? Pour old wine into new bottles? Is that even possible? Does that scale? You want to do incremental hierarchical generalization as the source of new categories. Now, we did experiment with an algorithm a decade ago to do this, but it was batch. Batch isn't good. Batch is unacceptable, right? You have to be incremental if you're going to be an organism. If you're going to do things like humans, it's got to be incremental. And then on the ontological side, look, QR benefited from centuries of mathematics, right? That's how come we know, hey, we covered ODEs, we cover a big ton of phenomena. what are the other things that might be out there for building more robust AI systems? Discrete actions is the one that gets me the most. So if you were going to like pick a random formalism, today it would probably be some flavor of PDDL, right? Before PDDL, it would have been strips. Are those really good enough? Are those have the same broad coverage in terms of phenomena? I don't know. And one of the interesting things that I've been thinking about a lot are discrete and continuous shifts in representation, because basically it looks like you alternate between continuous versus discrete ontologically when you're doing different things. And finally, if you want to play with this stuff, so SME has been publicly available for literally decades. This is the latest version, the one we're running, and it's been out there since like 2016. Documentation, benchmarks to test it with, commonless source code, and there's an executable with socket access if you don't want to screw around with common Lisp. Our NextQB knowledge base is publicly available, and Creative Commons attribution only, so you can put it into your own formalism. And we're actually going to be building a Python version of our analogy stack. Not because we're going to switch to Python, it's too slow, okay? But we want people to be able to pick the stuff up and use it and try it out with minimal pain. And in today's world, that's really the way to do it. One of our job candidates has 1.4 million downloads per month of his software. Okay? He's the QLoRa guy who's doing compression of deep learning systems. So I got some tips from him about, you know, making software go viral. All right, thank you.
We will have the Q&A session. Q&A session. Question and answer. Questions.
Yes, question.
혹시 질문 있으신 분 있을까요? Do you have any questions?
Thank you for the interesting talk. I'm very new in this analogy representation, right? So I have one question here is, I think the cost of creating these concepts might be high.
Oh.
I think, because if I see the PPT in the creating the images using some algorithms, this could be a single concept, but it can be we can use other representations to label these concepts. So anyway, my question is, how do you measure this cost of creating this concept? If, for example, if I'm building some application, I have to tell my customer we use have 10, maybe $10,000.
Why would you assume that? I mean,
Maybe.
oh yeah, I wouldn't. I think you're making some interesting assumptions, but I don't think they're correct assumptions. So, for example, in sketch worksheets, those are used by students as young as 5th grade, and mostly in college, and they draw, and the visual analysis is happening behind the scenes automatically. And so if they have a very complex sketch, it may take 30 seconds to actually compute feedback. But that's feedback they wouldn't get at all if they did it on pencil and paper. And so the students are very happy with that. The most real-time thing we do right now is the kiosk. So I didn't tell you about the language analogical QA training. But if you visit the computer science department, there's a kiosk hanging on the wall. And when you ask it a question, unless it's like where the bathroom is, that's hardwired, okay? But if you ask it a question like who's teaching AI, it's actually doing full stack language understanding. It's then using analogy MacFact to retrieve pieces of queries and using analogy to assemble those into a query and then answering your question. So in other words, the cost of encoding is the cost of encoding, and you can make that.
It depends on the application.
Yeah, it depends on the application. Yeah.
Thank
thank you for your short and implicative seminar. And I had one question. In the final session, you explained that qualitative reasoning can help human-like generalization, and you explained various methods, and one of the methods you explained is STEM reasoning. What does STEM reasoning specifically mean? STEM reasoning.
Oh, STEM, yes. Science, technology, engineering, and mathematics.
Okay, thank you.
Yeah, yeah. It's a term of art in education.
Yeah, thank you for the talk. I've never heard about this region of learning before, so it was very interesting to hear about. And I was wondering whether you'd done any experiments about how if the system generalizes any better. So you were comparing between the other deep learning systems before, of course, and I think those tend to struggle very much if you suddenly show them very different images that weren't from the original training set. Whereas I suspect that potentially this kind of system would be able to generalize much better because it's getting a structural understanding
Right.
rather than a pixel orientation understanding. Have you
Right.
found that to be the case?
Not yet. Yeah. There's, so for instance, Charlotte has this ARC challenge, and the problem is it's kind of a hack. I mean, all these things are basically figuring out sets of rules, and you're sort of fiddling around with toy domains. So the art is in the hypothesis generator as opposed to the understander part, at least in my opinion. I haven't looked at it that closely. He's now upped the amount of money to $1 million. So it might be worth looking at just to take his money. But yeah.
Any other questions?
So I think in terms of representation method in AI in general, we have a linguistic, predicate logic style of linguistic representation, propositional. On the other hand, the image icon style representation. Each of it is a representation. Here, I think it's more like a prototype style of case representation. You think?
Well, yes, but we actually build our cases out of predicate calculus, right? So, for instance, in the visual descriptions, those edge representations actually are bristling with assertions and relationships among the edges.
Right.
Into the compute edge cycles.
For example.
Hmm?
In Lisp.
Well, they're predicate calculus. It doesn't. The programming language is irrelevant, but so the structured relational representations in our cases for physics, problem solving, for language understanding, for vision understanding. The reason we've done several efforts on multimodal learning by reading is because literally the same knowledge base is used for the vision system as for the language system. And so the two of them have an easier time communicating, right? And we think that's true for humans too, right? We learn concepts that sometimes are visually grounded, sometimes more abstract. And if you're going to abstract out from everyday experience, then predicates are like the islands of coherence. Right.
Yeah. So anyway, I'd like to ask the possibility of transforming this kind of representations into deep learning style.
Well,
Connectionist like representations because it works in some way. If you have
well, right. So for instance,
training data.
So here's an example. In the companion language understanding system, it's a high precision language understanding system. So we can say things like, if the dam is open, 20 species of fish will become extinct. And so it produces a set whose cardinality is known to be 20, so it's an intentional set representation. It's got the counterfactual right about what the consequences are, okay. So it'll do all that stuff, which language models can't do, right? Because they just stay language to language. On the other hand, now you've got a social bot, and it's dealing with events. And these events have words it's never heard of because they're technical talks, they're job candidate talks, right? And so it's got really arcane, complex text. So the companion language system does not handle super complex syntax. It just does not. In fact, we're experimenting with using language models to simplify the syntax for it, right? Under program control, right? But like if you've got, new concepts, new words, and complex syntax, and people making cute jokes in the abstract and titles of talks, you're basically dealing yourself an impossible problem in any sort of finite language understander. So we cheat. We use embeddings. So like someone says, I went to Wednesday's machine learning talk. So I went to, and that basically says, okay, this is probably some event reference. So uses ChromaDB to compute a vector representation, checks that out against the things that happened over the last week, starting with Wednesday, because they did say Wednesday, and picks the thing that's most like it. So for in some cases, for practical purposes, we're quite happy to do that. But I think in terms of like the visual learning stuff, the only case where I've seen, I was thinking more the other way. So look, you've got these deep learning systems that sort of do some stuff, right? But for example, the coverage is actually pretty narrow. So you look at the things that are recognizing parts, they're like 20 different parts. That's nothing compared to the complexity of the things in this room, right? So what if you do what we've jokingly been calling cross-training in-house? So you basically start using analogical methods to try to learn better than deep learning classifiers for natural images. Because there now are a lot of good edge detectors out there. And so now if you run a lot of those edge detectors now, and you start doing SAGE on something like that, with the training being from existing deep learning modules, maybe you could actually use them as a sort of form of remote supervision. That's not something I want to spend a lot of time on because we get a lot more leverage out of just saying, hey, there's all this stuff we can plug into our ensemble and put it to work, right? But the high-level learning, we want that to be inspectable. Yeah.
We have catering outside after the shows, after the lecture. So please enjoy your dinner here. 그럼 오늘은 여기서 강연 마무리되는 걸로 하겠습니다.
Thank you very much.
Thank you very
Yeah.
much.
Thank you.